This is the second lecture in our Minerva Mini-course by Pierre Raphael, University of Cambridge. Basically. So today I want to talk about something. I really want to say a few things about what we know. In general, in Singularity. I'm not really talking about global distance criteria. I'm really talking about what kind of regime should we expect to end with singularity form. So this is something. There are beautiful answers that's been given on this for the heat equation. But there is a lot to this. In particular, there is a lot in there. Of course, maximal principle. Not on everything. There are many things that can be done without it, but actually there are a few key arguments that do rely on this. What I want to talk about today really is just my NLS equation. So in the focusing case, okay, so I have my data, and just to fix the ID for today, so say n is going to be dimension, so the critical scaling exponent is SC, so it's n over 2 minus 2 over p minus 1, say. And what I want today, I really want to focus onto the case when SC is between 0 and 1. Okay, so what can we tell in general? So we showed last time, right? I recall you this. I recalled you that the second derivative of the variance is equal to a certain number of times the energy minus another constant up plus 1, which immediately implies, and this is positive, which immediately implies that when this is strictly negative, the lifetime is finite. Okay, so this is the very argument. So we know that singularity formation can form. We ask, okay, so my classical solutions will break down. What should I expect? So the first thing that's completely trivial, of course, this is just Cauchy theory. So there are two things Cauchy theory tells you. Okay, and again, you think that my data are always in H1, okay? To begin with. So there are two things Cauchy theory tells you. Cauchy theory, because it's subcritical in H1, this is because I'm here, tells you that if a singularity form, then the L2 norm of the gradient must explode. So this goes to plus infinity, this goes to t. Okay, and in fact, you immediately have a general lower bound on drop rate. That is for free. That is the fact that, so I just want to make my numerology correct, the fact that if you want, this is a lemma. It's just this observation that, so this is something that's due to kind of Weissler, the fact that the L2 norm of the gradient must blow up at least like, so an exponent like this, 1 over t minus t to the 1 minus SC over 2. Okay, so why do I have something like this, which is just an artifact? The proof, and we're going to do a lot of this today, so the proof briefly is just the following thing. So you watch your solution, so u and t and x, and you say it's defined on the interval 0 t, and you say it blows up at t. Okay, so what you do, you renormalize. You renormalize this guy. So typically, you're going to define vt, so t is a parameter of tau and x, as being exactly lambda over tau to the 2 over p minus 1, u of t plus lambda squared t tau, lambda t x. Okay, so tau is mine. So t is just a parameter. So of course I've just written. So this is another solution of the NLS, and I choose lambda of t. such that I want the data for this guy. So I want vt at time 0 and x. Say I can take this in h1 dot. I renormalize this thing so that this is, say, equal to 1. Okay, which actually just means, if you do your algebra, just means that lambda to, so actually here I've taken, so this is lambda to the 1 minus s grad ut.
But this would be lambda of 0, right?
No, it's lambda of t. So t, no, it's lambda of t, okay? So t is just a parameter, okay? So I renormalize, so u is blowing up, okay? So I renormalize so that at time tau equals 0.
Yeah, this I understood. No,
so at tau equals 0, it's just this. So I just want.
Understand the choice of lambda.
So I just want. So this is my data. This is my new data. So the time is tau now. This is my new data at time 0. Okay. And what I want is that I want this data in a supercritical norm. Here I take L2 norm of the gradient.
So data is in tau, yeah.
Exactly. So I want this guy. I want my data to be of size 1. Okay. So it tells me how I choose lambda of t. Okay. So because it's a supercritical norm, okay? So this gives me this condition here, right? So when I put the dot, it's just the gradient in L2. Huh? So this condition here is telling me how to choose lambda of t as a function of t. Okay, and then the observation, of course, this is, so when I view this in tau, this is just another solution of the NLS, okay? Which initial data in H1 dot, which is a supercritical norm, is of size 1. Okay, so Cauchy theory tells me, because H1 dot is supercritical, Cauchy theory, right? H1 dot is a supercritical norm. So Cauchy theory tells me that this data must leave, there exists a universal time tau star, such that these solutions live at least until the time tau star. Okay? I'm sorry, it's grad ut in L2. Thank you. I should maybe put my grad in L2, and it would be more clear. I'm sorry. Okay. So what does it mean? It means that I must live at least until this time, this universal time tau star, which tells me that I cannot reach my blow-up time. So it means that t such that v, so v of tau and x lives on 0 tau star, which forces the fact that the lifetime, so t plus lambda squared t tau star, must be less than t. Okay, which is exactly the fact that lambda squared of t is less than t minus t. So maybe there is a divide by tau star, and I'm taking the square root. Okay, so every time you compute a scale, it must be smaller than the self-similar scale. Okay, it's automatic. Otherwise, you violate your Cauchy theory. So this is what we like to call this. This is the scaling bound. Please. So typically, I would do, so here, for example, I could do my Cauchy theory in H1. Okay, but I could easily do a Cauchy theory if I wanted to.
What do you mean by Cauchy theory? You just able to energy estimates?
Cauchy theory means when you solve, when you have strong solutions. Okay, so strong solutions are systematic. So it's exactly, it's systematic. It's a fixed point of this integral equation. Integral from 0 to t of e to the minus I tau u to the p minus 1 d tau. Okay, and my point is that you know from the Cauchy theory, because this is your fixed point argument, you know that the lifetime of the solution is lower bounded by something that depends only on something that must be a supercritical norm. Okay, so the lifetime t is lower bounded by something, a function that just depends. Typically here it would be the size of the data in H1. Okay, this is what I mean. But so this is exactly why if you blow up, L2 is conserved, L2 norm of the gradient blows up. So what's up there is automatic. It's given by Cauchy theory. Okay, it's given by this. So it tells you that this lambda of t here must go to a 0, and now what you have here is an upper bound. It must go to 0 at least with this speed. Okay, so this is something very general. Okay, so now essentially if you ask me what more do we know in general, it's going to be really pathetic because there is essentially nothing. Very few things, but I don't want to enter this. So let me say two things. So now I restrict, because this is mostly what I'm going to discuss today. I restrict, and I do two major restrictions. So I'm going to take radial data. And I restrict my range of exponents. So I want so I can make two things. Either n is bigger than n3, and then we can do the whole range 0 SC1. Or maybe you want to be in 2D, but then I need p to be less than 5 for obvious reasons in my subleth. Okay, so I'm definitely restricting the range of parameters, but essentially the initial target was really this. This is what we were interested in. So let me explain what's going on here. What is interesting here, this case is very interesting, because what's going on, again, you are sandwiched between two conservation laws. Okay, you have one conservation law here, which is mass, and one which is energy. And you're here. Okay, so you know from scratch, essentially, you know from scratch that this conservation law is going to be completely irrelevant. It will never tell you anything. But there is something very nice. You have a conservation law above, and everything I'm going to talk about today is essentially about understanding how to use a conservation law above. So of course, it's not always the case. It's because we restricted to this. But I think there is something interesting going on here. OK, so if I restrict to this, then there are two things I can say. So maybe I can make this a proposition. So proposition 1, which would be the following thing. So if I take an initial data, I say in H1. So maybe let me call this assumption H. So under H, so assume H. And so take a data unit in H1, and I assume that the corresponding lifetime is finite. Then there exists a sequence Tn going to T, such that I actually have an upper bound on the L2 norm of the gradient. It's controlled by 1 over T minus T to the alpha, and alpha is an ugly number. Alpha is 5 minus P over P minus 1 n minus 1. And if you do your algebra, you can check that this is always bigger. So this is always true. This is the scaling lower bound. So this is T minus T. What did I say? I say it was, what did I say? 1 minus SC over 2. But if you do your algebra, so this is always true. And this is just, and this is something, in fact, there is a space-time bound that says this. Okay, so there is an upper bound on blow-up rate, which is given by this over here. And the upper bound, so I should call it star, and star is sharp. Star is sharp, that is, there is a family, you can construct a blow-up solution that saturates this inequality. Okay? So I'm not going to tell you about this. I'm just going to, which in some sense, this is, so this bound, in many ways, it's pure algebra. So, and it's related to what I'm going to discuss today. But I'm not going to show you this. The fact that the bound is sharp is a whole story, which maybe I'll say a word about this next time. It's related to ring solutions. So there is a specific scenario that actually saturates this. The fact that we can show a bound that corresponds to the scenario is actually completely unexpected. But this is what's going on. Okay? Let me say one thing. In particular, let me make two things. Remark.
So this is only the spherical symmetric.
Spherical symmetry, absolutely. When SC is 0, in the mass critical case, there is no known general bound of any type. Right? And what I'm going to say is this kind of argument completely collapses there. So there is a huge gap. And when you go away from all these exponents, indeed, there is no bound in general. There are examples of blow-up solutions, but a general bound like this, I'm sorry, this is on the sequence, a general bound like this is not known. OK, so this is proposition 1. So in some sense, this is a construction. This is algebra. I'll say a word about this maybe next time, but this is not what I want to talk about today. Today I want to talk about something which is which is substantially different and which in many ways this is truly nonlinear. So this is proposition 2. So assume H. Take let U0 in H1 and assume that it blows up in finite time. Then the following holds true. Then if I compute the scale invariant norm, so I take the scale invariant norm, okay, then actually we can show that it blows up in finite time. And in fact, it's lower bounded by log t minus t to some power gamma, and gamma is universal. OK, so you should be worried that maybe there are constants floating around in this kind of estimate. So it's a typical thing, constant that may depend on the data. Of course, the data is in the picture. What depends on the data in this estimate is the time it takes to enter this regime. Okay? It's how long it takes to actually have this bound. That, of course, very strongly depends on the data. OK, so what is my point about this inequality? So there are a bunch of remarks that need to be done here. So first of all, of course, there is no a priori bound a priori bound on the scaling invariant norm. Neither lower nor upper. What I mean by that is that the very basic scaling argument that we did here, this renormalization worked because I knew how to renormalize in a supercritical norm. But if I do the scaling and I renormalize this, I'm not seeing anything. There is no lambda. Okay? So there is nothing for free. I mean, this estimate is by no means trivial. In fact, it's completely false. There is absolutely no obvious reason why this norm should explode. In fact, when SC is 0, of course, if SC is 0, then there exists a finite time blow-up data, of course. This is finite time blow-up data. Of course, this is just this is my virial argument again. But the scaling invariant norm, in this case, SC is 0, which means that the scaling invariant norm, U of t in L2, certainly does not blow up. It's conserved in time. Okay, so in particular, it's bounded. So there is no obvious connection between I form a singularity and my critical norm blows up or does not blow up. We have examples where actually it does not blow up and examples where this norm blows up. Okay, so it's not obvious. There is something here that needs to be not obvious, and it's false for SC equals 0. I would like to mention two other things. So there's been beautiful developments around this thing. So I'm thinking of a paper by Tao and Stokes, and a paper by Enur Bulut on the defocusing NLS. And what they show you, these are very, very nice work. I mean, this is very, very beautiful work. What these people tell you is exactly this. They tell you something which is a slightly different picture, but it's definitely connected. What they tell you is that if a singularity form for these problems, and of course it's not known for Navier-Stokes, we now know that it can happen for the defocusing supercritical NLS, at least in some regimes, then the solution breaks scaling. Meaning what? Meaning that, in fact, you can find an epsilon, which a priori depends on data, such that if you compute for the corresponding solution to the problem, if you compute the scale invariant norm, the SC would be my regularity, but in fact, you can allow for something little less, then this is going to explode. So maybe on a subsequence, I mean, I don't recall. I should enter this more specifically. I don't know if they have all time or if they have a subsequence in time. But this is definitely going, and there is an overall plan which goes into a similar way. Of course, estimates are different, but the methodology is related. So, and really, it's very interesting. It's telling you that for this kind of problems, and this is exactly what we show there, and I'm going to be more specific about this in the next lectures, singularity formation cannot happen. It cannot be a scenario of rescaling a bubble which lives at the scaling side. Something much violent must happen. That is, even if you normalize with the scaling, it should still explode. Okay? Something large must still be in the picture. So this is the second thing. The third thing I would like to say is that there is this immense series of work by Dukertz, Koenig, and Merle on the so-called soliton resolution conjecture for energy critical wave equations. For energy critical wave equations. And which essentially tells you that it's focusing, so it's typically wave maps and essentially what these people tell you is that any solution, so you need to be more specific, but essentially is going to decouple into a finite sum of bubbles plus radiation. And the point I would like to make is that in this problem, of course, the key of criticality is that in all this problem, the critical norm is under control. The critical norm, it's like in the L2 critical case, the critical norm for them is a priori bounded. And of course, this is an immense, I mean, this is a whole program, right, which has been completed really completely recently for wave maps. But the point I want to make is that the same argument that will allow us to prove explosion of the critical norm logarithmically here is the key to understand why, when the critical norm is bounded, the bubbles decouple. Okay? The fact that you converge there to a very specific object, this object that they call the non-radiative solution, is directly related. In some sense, it's the dual of this argument. In my case, critical norm is not under control. If I form a singularity, it must explode. In this case, critical norm is under control, and it's the key to understand the structure of the exact bubbles here. Okay? So there is really a common, at least part of the program is very much related. Okay, and the last thing I would like to say, and maybe this is something I would like to show, I think which is interesting to see work at least once, is that, so maybe this is my remark, this is 4, is that, and I think it's interesting to see this work once. There is a baby problem behind this, which relies on the rejection through Liouville theorem. And this has nothing to do with this problem. This is something that has been done and that is everywhere in regularity theory, being both for time-dependent PDE or elliptic PDE. This is this idea that to show any qualitative behavior, you can try to argue by contradiction and reduce yourself to proving some rigidity theorem. Okay, now I would like to go through these steps. Let me say, of course, the catch here, you see there are many works on trying to get upper bound on a norm. There are very little works on trying to get a lower bound on a norm, right? This has nothing to do with the linear estimate. What is being captured here is completely nonlinear, and the fact that you can actually get the lower bound, you can lower bound this quantity is not, what you need to do that, how to get the lower bound isn't clear. Okay, so let me show you how you enter a problem like this, which in many ways is something that people have been doing in very different places. So let me, maybe this is a strategy 1. And I like to show this because it shows you many of the problems that people have when they try to address this kind of question. And you will see that there is a gap between this strategy and what we actually want to prove. So strategy 1, reduction to Liouville-type. Okay, so let's see this in detail. So this should have been written somewhere over here. Exactly. So let me take my data, say it's in H1, and it goes up in finite time. So what I know is that the L2 norm of the gradient in L2 must explode as t goes to t. Okay, and I want to argue. So let me take a sequence Tn. So to simplify my life, I just take the soup because the gradient could explode, but this function could be very oscillatory. Okay, so I want to take a sequence which achieves the max. So I want that for all n, I want the gradient of u of Tn in L2 to be equal to the max of what I had before. Okay, so I want to take the worst. Maybe if it oscillates, I want to take the times where it's biggest. Okay, and I'll argue by contradiction. So I want to prove not the log. I want to prove that along the sequence, the critical norm explodes. I want to prove that the critical norm explodes. Okay, as n goes to infinity. And I argue by contradiction. Let's assume it does not.
So again, the critical norm is between 0 and 1.
Exactly. SC is between 0 and 1. Okay, it's really just think it's your, right, it's just your favorite. So SC is always between 0 and 1. Okay. Okay, so by contradiction, assume it's bounded. Assume a bound. So uniform bound in N, so assume that my critical norm along this sequence remains bounded. Okay? Then what you want to do, so now I rescale my problem. So rescale the problem. So what I do is I define, so this is exactly the same rescaling repetition. So I like to think of this, so this is a sequence of initial data. So I define un of 0 and x to be lambda u of Tn to the 2 over p minus 1. So this is just my initial data. So this is u of Tn lambda u of Tnx, where I choose lambda u of Tn such that, so what I want I want the L2 norm of the gradient of my data in L2 to be 1, which tells me that lambda u of Tn, so this is always the same formula, it's going to be 1 over the L2 norm of the gradient of u of Tn in L2 to the power 1 over 1 minus SC. Okay, this is just renormalization, and of course this thing goes to 0. And of course this thing is going to 0 as n goes to plus infinity. Okay, because SC is less than 1, this is my supercritical. So of course now you see key 1, I have a conservation law above. Conservation law above. Okay, I know that one thing is so I know that the energy of u and naught is equal to what? It's equal to lambda u of Tn to the power. So I just do my rescaling, so you will get twice 1 minus SC, the energy of u of Tn, but the energy is conserved. Right? So this is the energy of data. Okay, so this thing is going to 0 as n goes to plus infinity. Okay, so this is key number 1. I have a conservation law above. Of course, when I renormalize my conservation law, because it leads above, automatically my conservation law crashes. So the energy of my new data is converging to 0 as n goes to infinity. Okay, so this is right. This is really, if you try to do this in L2, you will see that of course you lose control of the L2 norm. So L2 is completely lost. There is no way you will control the L2 norm of un. Of your sequence of initial data un of 0. Okay, and of course by assumption, so I assume, so this is my assumption. By assumption, and because this is scaling invariant, of course the HS critical norm of SC is, this is un of 0. This is nothing but the critical norm of u on the sequence Tn, because it's the critical norm, and I've assumed it's bounded. Okay, so I have a bound of un naught in h1 dot and in h dot sc. Okay, so in particular, so I can extract the weak limit. Right, I can extract the weak limit because I control in hsc dot and I control in h1 dot, so I can extract a little limit un naught weakly converges to someone, so how did I call it? I called it V naught. So this is really up to a subsequence. So this is in HSC intersected H1 dot, okay, as n goes to infinity. And you understand you have to abandon L2. L2, there's no way you're going to control un naught in L2. It's out of control. Okay, so this guy, so I have my weak limit in H1 dot intersected with H1. Of course, you know that when you have a weak limit, you better be careful. So you want, of course, the weak limit to be non-trivial, so you want V0 non-trivial. But this really follows from your conservation law, because remember that the energy of un naught, so this is going to 0, but it's equal to 1/2 the gradient of un naught squared minus 1 over p plus 1, the integral of un naught to the p plus 1. Okay, so this is in Rn. Sorry, this is Rn. But you've renormalized. Okay, you've done what you had to do. This is equal to 1 because this is the definition of your renormalized sequence. This is going to 0, so it means that the un naught to the p plus 1 is actually going to whatever number, non-trivial number, as n goes to infinity. But now I am with radial data. You know your Sobolev. I'm using radiality. So let's say that I do everything in 3D to make my life easier. So in fact, the embedding, right? So I have that hs dot c intersected h1 dot is going to embed. So I suppose it's it's going to embed compactly into the LP plus 1. This is because it's radial. Okay, which tells me that V naught is non-trivial. okay? Because the LP plus 1 norm of V naught is going to be non-trivial. Okay, so this is a cheap way to use radiality, and by passing to the weak limit, of course, this goes to 0, have weak convergence here, but this strongly converges. Okay, this is the classical argument. Then it tells me that not only am I non-trivial, I have energy which is non-positive. Okay, it's just, again, it's just weak limit here, this goes to 0, and strong limit there. Okay, it's just my radial Sobolev. Okay, but so that's for my data. Now, as a matter of fact, I know something more. As a matter of fact, so you should think of it this way. So I have UN naught, it's equal to lambda u of Tn to the 2 over p minus 1 u of Tn lambda u of Tn. Next, that's the definition. And I've showed that this weakly converges as n goes to plus infinity to some initial data v naught. So this is in hs dot intersected h1 dot. Okay, but I know the flow. I know the flow generated by this guy. Of course, this data, this is just rescaling by this factor here. So I know that the corresponding solution to NLS is nothing but lambda u of Tn to the 2 over p minus 1. So I'm going to have u of Tn plus lambda square u of Tn tau lambda u of Tnx. Okay, and my point is the following thing. And so now I can compute, of course, for all tau. So you see the lifetime of this guy is bigger and bigger. So when am I, so I am, because this starts at 0, so this is minus Tn divided by lambda square u of Tn. And I can go to a 0. So where do I have on this interval? I have that the L2 norm of the gradient of un of tau, so you compute that. So you just renormalize. So you will see this function lambda u of Tn, and then just the same function, but evaluated at Tn plus lambda square u Tn tau. Okay, so when you do your algebra, you get exactly that this is equal, if you want to, it's just meant to be. It says grad of u at the time Tn plus lambda square u of Tn tau in L2 divided by the norm of grad u of Tn in L2. Okay, but now tau is negative. Right, so this is less than Tn. So you remember this is what I asked the sequence Tn. I asked the sequence Tn to be such that whatever is on the left is smaller. Okay, so this guy, by construction, is less than 1. Okay, this is the choice. And this is exactly, this is where I choose. This is because Tn is some maximal sequence. Of course, if I had oscillations there, I mean, I could run in troubles. If I took another sequence Tn, it's not clear. But so this is a consequence of the maximality of the Tn sequence. Okay, and of course, and just by a renormalization, of course, the un of tau hs dot sc, for exactly the same reason, because it's bounded here along this sequence, is going to be bounded. Okay, so what do I have here? It means that if you want un of 0, I can pass to the limit, get a v of 0. Then this generates a solution of NLS, which is un tau of 0, which leaves on a type interval tau, which is minus Tn over lambda square u of Tn. So you understand, Tn goes to some finite value, lambda u of Tn goes to 0, so this goes to minus infinity. So it leaves on this, and in fact I have bounds on all this interval. I have bounds on un of tau. Okay, so now it's an exercise to show that this diagram can be completed. That is the fact that the solution, if you want to NLS, generated At the weak limit, you can extract the weak limit from this guy, which is exactly the solution to NLS generated by this. It's just, again, it's just Cauchy theory. But you have to round out H1, but there's no problem in doing it in H as C dot intersected H1 dot. Okay, and then what you have, so the outcome, what's the outcome? The outcome is that you have, so you have V of tau. It's a solution to NLS, which satisfies three things. One, it's defined, so it's globally defined on minus infinity 0. And second, its energy is non-positive. Okay, and of course you have, boundedness. V naught is in H1 dot intersected HS dot. Actually, you have more. You also have gradient bounds if you want. I mean, you know a bunch of things on this thing, but this is the heart of the matter. Okay, so this is what I call a Liouville theorem. Liouville theorem is by arguing par contradiction. You pass to the weak limit, you extract an object which satisfies a bunch of property, and then you show that this is nonsense. Okay, so this is the Liouville rigidity theorem. I have no idea. It's an excellent question. I don't know. Maybe he proves some rigidity thing, or it's a very good question. I don't know. But this is, please.
Yeah, I mean, you have a global solution.
Yeah.
Like a typical Liouville theorem, you have a harmonic function which is bounded on the plane, so it can only be constant. You're doing the same thing here.
But why Liouville? Why the name Liouville?
By analogy.
Because Liouville proved this one. This is what you did. This is what you told me. Okay.
Liouville is part two. I mean, you did something, and then part two is Liouville.
Part two is Liouville. Part two is exactly this. So this is, if you want, theorem. So this is exactly this. This would be the Liouville.
So that's one.
Yeah, that's here. That's the rigidity is here. Yeah. So the Liouville is this. So under H. So this means typically think that I'm doing 3D 0C1 radial. And then take a data U naught in HS dot intersected H1 dot. Okay, so there is absolutely no problem in removing L2 from your Cauchy theory. This is completely irrelevant. Making strong solutions here is, this follows from Strickart. Immediately there is nothing, I mean, there is no, you can definitely work there. There is unique class of solution here. So the claim is the following. If the energy is non-positive, then lifetime is finite. Okay, so you get your contradiction. Okay, why? Because remember, NLS is a reversible problem in time, so you cannot leave here your global on the left. No, but it can't. It's impossible. You have to blow up. If I say this, it means that, of course, I can revert time by, so it's reversible. So it means that you blow up on both sides in time. Okay, so this cannot happen. Okay, so if you can show this, then this shows that the norm must explode. So how could you hope? I would just like to make a bunch of remarks. And these remarks are related to what I'm going to say later in the class. So remark. So how trivial is my Liouville theorem? So observation 1. So if I take a data which is in the Villiers space, so this is XU and L2, and say, I mean, I can take HS dot intersected H1 dot if you want. So this would be H1. So actually, it's automatic. So now I can put H1. So if I have integrability of L2 if you want, then this is completely trivial because, again, I have the virial law that's telling me that x squared u squared is less, essentially, than 16 times the energy minus something like this. Okay, so if the energy was strictly negative, then of course I must blow up in finite time. Okay, so if I have integrability of data, it's completely trivial. So here I don't have clearly the problem is really zero energy. So if you have zero energy, so it's an exercise. You know what you're going to do, and this is exactly how the analysis is going to start. If the energy is zero, then of course you can localize the virial identity. And if U0 is in L2, you can easily see that this is just Sobolev. That's an exercise. That energy non-positive implies that you have a lower bound on U in L2. You cannot disappear. This is lower bounded by a function of data, strictly positive. And because of that, it's very easy to conclude that T is finite. Okay, but here I'm using my conservation law very strongly. Here I'm using my conservation law. In L2. Okay, that's an exercise. So now you're going to tell me, okay, but then this means that your theorem is completely trivial. This is just about doing similar things like Ogawa and Tsutsumi did 30 years ago. Just localize this thing and you will get what you want. So let me say that it's not the case, because there is a very serious problem. You have to be very, very careful here. So this would be remark 2, careful. And this is something, so let's take the time to do this computation, because I'm going to do that all the time, starting next time. So let's talk about self-similar solution. So what is a self-similar solution? So what I want to call a self-similar solution is something that formally blows up. It's something that blows up exactly with the scaling of the equation. So what I mean by that is the following thing. So I really want to solve my PDE, I dt u plus Laplace u plus u modulus of u to the p minus 1 equals 0. I want to solve this exactly by making an ansatz I want to make an ansatz. I want to say that u of t and x is exactly equal to 1 over lambda of t to the 2 over p minus 1, some profile which I'll call p of x over lambda of t. And maybe I allow for a phase here, because this is an LS. And let's just take lambda of t to be exactly the square root law. And typically gamma of t will have we need to take some log, something like this. And then if you do your algebra, what you will get is exactly this. Because you do not allow p to depend on time other than with this x over lambda dependence, if you let y to be the rescale variable, what you will end up with here is exactly, and because you chose this to be exactly the square root, what you will end up with is the following thing. So you will end up with this thing, Laplace p. So maybe p is not such a good idea. Let me call it, I don't know, r. So you will have Laplace r minus r plus I over 2 over p minus 1 r plus y dat grad r plus r modulus of r to the p minus 1 is equal to 0. Okay, so every time you can find a solution to this, which functions and in whichever function space it is, every time you have a stationary, so this is really a stationary problem, there's no time here, then it generates automatically an exact solution to the NLS. Okay, so I'll discuss the question of existence of self-similar solution is a complicated problem, even just for this very simple NLS model. But I will just like to say the following thing. There is very clear, so there are some cases actually. So when SC is 1, we know how to construct, such profile. We know how to construct solution to star. And in fact, it's widely expected that they exist for 0 SC1. Okay, and what do I mean by that? Well, of course, there exists solution. I mean, if you think that R is just a radially symmetric function, there are always solutions to my ODE. What I mean by existence is that the smooth solution at the origin is going to decay at infinity. Right? This is the non-trivial part of the problem. So in particular, if they exist, or when they exist, it's easily seen that R of y, so think that it's a radially symmetric function, is going to behave as y goes to infinity like some constant divided by y to the 2 over p minus 1. Okay, why is it so? It's written here. You see, if you decay at infinity, then this is going to be lower order. So you will be driven by the so think that everything is radially symmetric. You will be driven by the fundamental solution of this thing, which you can compute, and it's going to tell you that this is the decay that you expect. Right? So if you want existence of a self-similar solution, it's think of it as an ODE problem. If this is modulus of y, all I'm saying is that you're looking, so this is R of y, you're looking for, it's a shooting problem. You're looking for the value at the origin such that asymptotically you behave like 1 over y to the 2 over p minus 1. Right? If you shoot something else, you'll get mad, but there are maybe special values for which this can happen. Okay, so again, sometimes we know how to prove that they are there, but it's widely expected, in particular from numerics. There is numerical evidence, very clear numerical evidence that these guys exist. So why do I mention these guys? I mention these guys because, again, it's an exercise. What difference
was this in for critical expansion for when SC is 0 or 1?
Different world.
So
it's a different world. SC equals 0, SC equals 1, it's a different universe. Yeah, this is actually, this is something, okay, so let me say this. When SC is 1, when SC is 0, this is d over 2. Okay, you take this, you hit with R bar, and you look at the imaginary part. Everything cancels, and what you get here is that this decay produces a boundary term in the integration by parts, which means that these guys cannot exist. Okay, so when SC is 0, at the critical case, there is no self-similar guy. In the wave map thing, which happens when S, but there cannot be anything else. If you decay, it must be like this. Okay. So there is no self-similar guy at SC equals 0. Same thing at the energy critical level. Blow up for wave map is never at the critical level, and in fact, it's a term. It's part of the asymptotic description of Ducard, Koenig, and Merle. You cannot, it's the beginning of the proof. You cannot have self-similarity. You never have the self-similar speed. But it's exactly because of this, because the critical norm is bounded. This is what generates that. You move away from this, you relax the control of the critical norm. I'm not saying this is the mechanism, because we know other mechanism. It's one mechanism. Okay, but this one cannot exist in the critical setting. Okay? So let me go back to this case. So SC is between 0 and 1. So why do I mention this guy? I mentioned this guy because once you have a profile like this, it's very easily seen that its energy is 0. You know exactly what you want to do. You want to hit, because what you're going to do, you're going to get star, and you're going to hit with the Poiseuille multiplier. You're simply going to hit by 2 over p minus 1 r plus y. You're going r, and it's going to give you exactly this. Okay, so this guy is a candidate to have 0 energy. It's very easily seen that r is in h1 dot. Okay, so it's a zero energy solution in H1 dot, but R is not in HS dot. But why is it not in HS dot? It has nothing to do with regularity. This has to do with decay. Because this decay, think of it in LPC sense, right? I'll send HSC to your favorite, the other way around. No, this way, to your favorite LPC. Okay, then this decay is exactly the one that's going to give you logarithmic divergence. Okay, so you're just missing, right? So you miss critical space by a log. Okay, but however, okay, so they are not. So remember, I'm supposed to prove my Liouville theorem. What I want to prove is that if data is in there with radial symmetry, etc., and energy is negative, then I blow up on both sides in time. T is finite on both sides. Okay, so of course these guys, they are not a contradiction to my theorem, because indeed the energy is zero, but they are not here. They just miss this by a log. But what's the corresponding solution to NLS? So if I take this guy, it's 1 over lambda of t to the 2 over p minus 1. It's this profile r of x over lambda of t, and lambda of t is square root of t minus t. Okay, so the point I want to make is that this guy, if I look at them backwards, that is, if I send t to minus infinity, right, they are global in time on the left. And actually, they don't blow up, they spread. Okay, so it means that if I relax this by a log, I have a counterexample immediately. Okay, so do not think that you're going to integrate by parts in your very identity and trivially get the answer. It's completely false. You have an example right below your eyes. Okay, so if you want to prove that, you need to capture the tail. It's all about, you need to capture the tail. Okay, and this problem is everywhere in singularity formation. It's all about the tail. Okay, this is what you need to capture. So this statement is about the tail, and the fact that you blow up logarithmically, of course, is exactly, in a way or another, seeing this thing here. Okay? Okay, so this was just... So how about we do 5 minutes break? Excellent. And then we start proving this, okay? Let's make a small break. What's wrong with my phone? You know who this is, right? Oh. No, can't be.
Frank?
Of course. No, that's my son, this time. Okay, I'll just email him that I can't. Not sure, yeah. He sends me. This is my life now. So, let A diagonalizable, show that the action is Q-Puzzle, unique solution. Okay, that's easy. But show that there is a unique cubic root. I mean, how I'm supposed to know this? This is my life now. No, it's not part of it. Bathroom here, go. I should go up.
Go up to the second floor.
Okay, and left.
next Sunday.
Yeah, next Sunday is perfect.
For a brunch.
For brunch, excellent.
Okay.
You want to go downtown or?
No, we'll be at our home.
Okay.
We just finished our home stuff.
Okay. Then send me an address and next weekend we'll be coffee.
Next week, okay.
Okay, excellent.
Fantastic. Okay, so I apologize, but we should chat about these sort of things.
Anytime.
Yeah, okay, so I'm here. I mean, Monday, Tuesday. I think Monday for sure I'm here. Monday, Tuesday I'm here.
You should.
And sometimes at the end
Just
of the week.
I'm there all the time, Sergio. Just send me an email.
I'll send you an email.
I'll be more than happy to chat. See you.
I can't defer. It's a bad way I can defer.
I feel like you guys are opening me up. Yeah. Like I did like more than 3 minutes, and I got restricted from the first round.
So should we go again? I have a lot to say. If you take too big a break, I'm not giving a break ever again.
That's what happens.
But I probably won't be able to. That's often enough.
Okay.
Okay, so let me, so in all what I'm going to talk about, so the enemy is very clear. The enemy is this guy. So it's 1 over lambda of t to the 2 over k minus 1, r of x over lambda of t. And lambda of t is the square root. So in particular, what I'm very worried about is my gradient that goes to 0 in a self-similar way. Okay, that's the enemy. And you understand, from scratch, let me say that the enemy has nothing to do, it's not the linear enemy, this is the nonlinear enemy, and this is, so there's not a single estimate that comes from the linear flow, it's all bound onto, ruling out this guy. Okay, so let me maybe to motivate, let me start with the basic estimate, which is nothing but the celebrated Morawetz identity in a way or another, which of course can be just thought of as the localization of the variable identity. And one of the reasons also why I want to show this is that because you will see there is one estimate essentially in everything you do, one estimate, but a little bit tortured. And I think it's amazing how with just one estimate you can actually do many things, right? And this is a lesson. When you have one estimate, maybe you're not using it properly. Maybe there is more than you think. There's really, it's a question of understanding what is the use of this estimate. Okay, so what's the basic Morawetz identity? So again, I just want to localize the variable law. So instead of computing this, I'm going to take psi. So everything has radial symmetry. So I'm just going to take psi of x. So that's my cutoff function. I'm going to tell you in a minute how I choose it. And so actually, I called it chi here. So let's just call it chi. And then what you do, so instead of taking chi equal x, you compute ddt of the integral of ku squared. And maybe there is a half. It's equal to imaginary of grad k grad u bar. Okay, and then you compute this, ddt of maybe there's a half imaginary of grad k grad u bar. Okay, so this is the celebrated identity. So you get k double prime. So these are all integrals over Rd. You get k double prime grad u squared. You get minus the quarter, the bilaplasian of chi modulus of u squared. and you get something which I will write here. You get minus a half minus 1 over t plus 1, the integral of Laplace chi modulus of u to the p plus 1. Okay, and along the way, I use radiality here, because otherwise it's a little bit more complicated, but this is sort of the flavor of this kind of estimate. Okay, so this is just a brute force computation. So what I can do, so I can take, so I just don't recall, did I take exactly? So I take the following scaling. So I take psi of x to be x squared over 2, say for x less than 2, say. And I can bring it back for, I do something very violent. I just bring it back to 0 for, I'm sorry, this is French, for x bigger than 3. Okay, and I can always do that in such a way that grad psi square is less than a constant psi, and psi double prime is than 1. Okay, and then I define, if you give me a parameter r, so this is the classical renormalization, so if you give me r, I just take chi to be what I call, if you want, r square psi of x over r. Okay, so this is just a thing that's scaled the same way, so it's just x squared. So this is just x squared until r, and then I bring it back maybe until 2r maybe, and then at 3r, I just bring it back to 0 in any stupid way you like. So this is chi. Okay? So let's see. So if I do that, let's look at the terms here. So what can I do with chi double prime? So not much. So this is the localized term. All I'm going to say, I want an upper bound. So I'm going to bound chi double prime by 1.
Do you mean that inequality grad psi squared is less than constant times psi?
Yes, because it's a square, right? It's true at the origin.
What happens at the first point where psi vanishes?
You're right. I don't care for this. No, I think actually it's okay, but because it's but I don't need that. Right. All I need is psi double prime less than 1. This is typically when you bring it back to 1. This is what you use. But when you bring it back to 0, yeah, maybe. But I will not use this. This is irrelevant. Okay, so let's just look at my terms here. So I'm just going to use, so this I just bound by 1. So I have 1 half ddt of imaginary, so I have this grad chi grad u bar. So I bound this by grad u squared. Okay, and then I have this term here. So of course the bi-Laplace is just something that involves only derivatives of chi. Okay, so this means that I can simply bound this. Maybe I have a constant, the integral from say 2r x between 2r and 3r, and of course there is a factor 1 over r squared, because this is my scaling, so I have r squared, this is 4 derivatives, so I have something like this, and I have a universal constant here. And then I have minus, so this is where things, so I have this thing, so I have minus 1 half minus 1 over p plus 1. So I have the integral of the Laplace psi r. So this is chi. So I can think of it this way. I can say this is Laplace psi of x over r modulus of u to the p plus 1. Okay, so I can simply play a simple game here. I can here if I like, I can put all the LP plus 1 norm times the constant that I would get if psi was x squared over 2. So if I made this correctly, this is exactly, this would be exactly d. So I can say that this is less than grad u squared, right? So if psi is x squared over 2, so this is just going to be d. So I have grad u squared minus, so this is n, sorry, n, 1 half minus 1 over p plus 1 times the LP plus 1 norm, and it costs me it costs me, so I just bound, plus so it costs me constant over r squared integral from 2r to 3r of u squared, and it costs me some universal constant independent of r, this is what I'm counting, the integral for x bigger than r of u to the p plus 1. OK? So now you play with your supercritical numerology, and you realize that it's the same thing when you do the Virial law. If you want 1 minus n, 1/2 minus 1 over p plus 1, the integral of u to the p plus 1, you just trade this for energy, and what you get is exactly this. You get n times p minus 1 over 2, the L2 norm of the gradient. Exactly. No, it's not. It's the other one. I'm sorry, because otherwise I'd be in trouble. So this is exactly the energy. I want to pay the energy. So the energy is conserved. This is the energy of U minus twice SC over, I'm sorry, this is N minus twice SC, the integral of grad U squared. OK? So I've proved. So if you want, this is the localized version of the Virial law. So this is if you, I'm sorry?
It's not equal to that. Well,
This is equal to that. I'm just injecting this. I'm just trading for energy. Then I feed it over there, and I've proved an upper bound. Okay, I've proved something completely trivial. I've proved. So if you want, this is the completely algebraic lemma. I've proved that. So just to write something correct. Yeah, I've proved exactly this. I've proved that there is a universal constant c, so it's the SC over n minus 2. So I have c times the integral of the gradient plus ddt of imaginary x dot grad u bar. This is controlled by a certain number, another number c times the energy of data, and it costs me 1 over r squared, the L2 norm between 2r and 3r of x squared, of u squared, plus the integral for x bigger than r of u to the p plus 1. Okay, and this is where you see that I have a nonlinear problem, right? This is this trade-off. Grad u squared is on the left. Okay, so this is going to be the way to control dispersion. So this is the fact that it's on the left. It's really because it's nonlinear. In other words, you never have non-positive energy for a linear problem, right? Because u is small. Okay, so this is an estimate. So we're going to do nothing more than integrate this over and over again. But you need to see something. So, so there are several ways in which I can. So maybe let's just continue following this. So why do I need to estimate in this? I need to estimate. You see, I have p sub L2 norm on an annulus, and then I have the UP plus 1 norm there. Okay, so I need an estimate to control these guys. So if you ask me, so maybe I wrote it here. Let me check on time. If you ask me to control, okay, so let me put it this way. So control of the nonlinear term. Okay, so of course I can do something stupid. I can just, if you want the sub F, it's just going to tell you, if you want to interpolate the u to the p plus 1 norm, you certainly have your Gagliardoni-Heinberg is going to tell you that it costs you, if you want, the critical norm to the power p minus 1 times the integral of grad u squared. Okay, and of course you understand that, so this is just Sobolev. So you understand this estimate is a disaster because this is supposed to grow, so you're never going to control your gradient on the left. This is a dead end, okay? This is a dead end. At least if you try to use it there, okay? So I need something. I need to use radiality, of course, and I need to use the fact that I am away from the origin, okay? So there is an observation, which is a fundamental observation, which is that you see this type of norm here, pieces of L2 on an annulus. If you think of your enemy, which is the self-similar solution, of course, the critical norm is infinite. But if I start integrating 1 over R on an annulus, I get bounded again. Okay? So in fact, there is a norm, which is a very convenient norm, which is a classical Morawetz type of norm. Right, so maybe I should, yeah. So let me define, so let me make this a definition. So this is the Morawetz weighted L2 norm. So let me define rho of U and R. If you give me an R, I just take the sup for R prime bigger than R of, so I just do something scale invariant. So 1 over R prime to the twice SC integral from X between, say, R prime and twice R prime of modulus of U squared. Okay, so I just take my L2 norm on annuli, okay, and I weight this by the correct factor to see my, so that it's scale invariant, and I take the sup for R prime bigger than R. So in particular, this is a decreasing function of R. Okay, and then if you want lemma, so the radial Sobolev, which tells you the following thing. So I can make a scaling invariant estimate, which of course breaks, so it's scaling invariant, but it breaks the curse of the grad U square here, just by saying the following thing. So first of all, of course, I have for all R strictly positive, just a trivial thing. So the 1 over R to the twice SC integral for X less than R of U squared. This is certainly controlled by a constant independence of R, C norm of U LPC squared. Now what I call PC, it's the critical LP norm. Okay, so it's the one that corresponds to my Sobolev. Right, so it's just that H dot SC embeds into LPC. Okay, so this is completely trivial. This is just older, which is a little bit less trivial. But it's easy. You just cut into is that the limit when R goes to plus infinity of 1 over R to the twice SC integral of U to the square. This goes to 0 as R goes to plus infinity as some as U is in H dot SC. Okay, because you just cut into. Okay, so this is estimate 1. And the second estimate, which is exactly what I'm going to use here. So if you want, this is you know, if I was in a general setting, this is what people like to call a precised Sobolev inequality. It's simply this observation that if I compute, the integral for x bigger than R than U to the P plus 1, then I can bound this, say, by a constant eta, the L2 norm of the gradient of U, plus another constant, which depends on eta, times I have something like this. So I have rho of U and R to the power. So actually, it's the whole rho that is to the power P plus 3 divided by 5 minus P plus rho of U and R to the power P plus 1 over 2. Okay, so you see what's going on here. So of course this is, okay, so maybe I don't have time to show this, but this is completely elementary. It's always the same story. You use the fact that outside of the origin, you behave like a 1D function. Okay, so you will see your Sobolev in 1D. You have to count the weights. You have to understand how this thing is counting. But you see here, of course, this exponent is telling you, of course, this is where the P less than 5 constraint is essential. If you want, it's the L2 critical constraint in 1D. It's just telling you that if you're in 1D, if you want UP plus 1 to be interpolated with an exponent here that's less than 2, you don't have a choice. P needs to be less than 5. Otherwise, it's a different one. Okay? So of course, and what I should say is that for any eta, there is this c eta, and this estimate is completely scale invariant, so it's true for any r and any u. Okay? So the constant do not depend neither on eta and c eta. I can choose them. Okay, so you see immediately what's going on here. So this is, of course, a machine to estimate, right? To estimate the right-hand side here, so to absorb the gradient term and pay for something like this. Okay. So what does it mean? It means that, roughly speaking, what you're going to get is that if you control this norm, essentially, you can hope to control the gradient with respect to this kind of quantity. Okay. On the other hand, remember that ddt of chi u squared is equal to the imaginary of grad chi grad u bar. Okay, meaning what? Meaning that if I integrate this twice, on the left-hand side, I'm going to see my gradient, and I'm going to see this guy here. Okay, but this guy, of course, chi, remember what chi is. Chi is nothing but x squared brought back to a 0. Okay, so it's x squared until 2r, and then maybe at 3r I bring it back to 0. So in particular, I control this quantity is going to be under control here. I'm going to control the L2 norm here. Okay, so what I'm telling you is that when you integrate, you can control everything by this rho norm, which is on the right-hand side, but this rho norm is also on the left-hand side. Okay, so this is a machine. This is a machine to control the rho norm. Okay, so what I'm telling you is that this is not a conservation law, but there is this identity, just the Morawetz identity localized in a suitable way and using this kind of interpolation estimate will give you some sort of a priori bound on the rho norm, which of course is a scale invariant norm. Okay, so maybe let me make a statement. So maybe I'll write it here. I'll try not to erase it. So the way it goes is as follows. So if you want, this is proposition 1. So there are really two essential propositions. So proposition 1. So let's try to say things that are correct. Okay, so take, say, v of tau, which is, which leads on some time interval 0 tau star continuously into HSC intersected H1 dot. Okay, I take a nice initial data there. Of course, I'm radially symmetric, etc. SC is between 0 and 1. And I make the following assumption. Assume two things. Assume that the time tau star can be compared to the energy of the data. So max of the energy. So you should think that I'm really interested in non-positive energy. So this would be, so this is a bound on the time. So assume this and assume that m naught, which is for v naught, I should say it like this. I assume, just to make things simpler, I assume that the size of the data in HSC is bigger or equal to 1. This is mandatory. I mean, if you want, this is automatic. If energy of V naught is non-positive and the L2 norm, the gradient of V naught is 1. Right, so anytime you have a non-positive energy, you will normalize it from above, and it's automatic from Sobolev that you must be big in the critical norm. This is a big guy. Okay, so I assume this, then the conclusion is the following. If you look at the rho norm on the scale V of tau star, which is m0 to the alpha 1 square root of tau star, then it's just bounded by a constant times the size So this is M naught. What I call M naught is this. Okay, so it means that I have a bound. You see, this is the key estimate. I certainly expect that the critical norm wants to run out of my hands. Okay, but I'm saying that this rho norm does not. Okay, at least as long as I control this guy is under control. So it's not a conservation law forever. It's definitely a bound that leaves as long as this is true. Okay, then this is true, and I have what we call a dispersive estimate, because you have to think in the back of our mind that our enemy is the global guy to the left, which gradient decays in a self-similar way. So what we claim is that indeed this needs to happen. That is the integral from 0 to tau star of tau star minus tau times the L2 norm of the gradient of v of tau in L2 squared d tau. This is bounded by m0 to some power tau star to the 1 plus sc. Okay, so the numerology is forced upon you. I mean, this is just because everything is scale invariant. So if there is an estimate, there can be no other. Okay? And maybe just to make this, the proof of this is simply, the proof of this, if you want, is you take a time. So you pick tau naught in 0 tau star, okay? And you define the soup. So A being given to you, A given. You define this to be the soup. So this is just the max over tau in 0 tau naught of rho at v of tau a square root of tau. Okay, so you look at the size of the rho norm on parabolic cylinder, okay, and you consider the soup. Right? You take this quantity to be the soup of a tau and tau. So in other words, I'm running a bootstrap here. I'm saying give me a bound on the rho norm. This will allow me to control this, and now I can integrate twice. Okay? So pick this time, define this like this, and then just, and run this. Let's go star, and run star with R to be exactly a square root of tau naught, and A will need to be chosen. Okay, and then once you have this, and then integrate, so you get an estimate. So you get a differential inequation which is true for all tau in 0 tau naught. Okay, and when you integrate this differential inequation, what you will get is a bound. So what you get is a bound of the integral from Rx to R of modulus of u squared at tau naught, which you can divide by R to the twice sc. You get a bound on this in terms of itself. Okay, because you will get exactly, you use your interpolation bound, and you will, so what I'm saying is that you will get control of this norm in terms of itself, but of course there is a power, to some power. So you understand what's going on, it's a bootstrap. You can say, if this thing, you will say, if this thing wants to be of size 1 over epsilon, so initially it's of size 1, say, if it wants to be of size of 1 over epsilon, in fact, what I will contract, I will prove that, in fact, it will never be worse than 1 over 2 epsilon. Okay, and so I cannot get out of the regime which is here. Okay, so it's really, if you want, it's a trapped regime. Right, so you have to understand, and this is a classical thing, scaling is not broken. What is broken here is the numerology, this number here. Right? Here I have a square, and here I have something else. And that's the key. Okay? Okay, so this is I mean, once you see this, it's just a question of sitting down and making it work. So this is our first proposition, the fact that on parabolic scales, I have a bound on this rho norm, which depends only on data. Okay, and of course you understand where this assumption comes from. It's just that when I integrate twice, right, I have my energy on the right-hand side. When I integrate twice, I just did bounds on this. So this is where this condition comes from. Okay, so this is proposition 1. So now I can say something else. So there is something very nice in the estimate there. So this estimate does two things for so proposition 1 does two things for us. One, it controls the rho norm. And two, it estimates the gradient. Right? And as soon as you estimate the gradient, what you can do is you can, what we like to call, you can integrate L2 fluxes. You know, because again, it's just this observation that, you know, ddt of the integral over Rd of ku square is nothing, so there's a half. It's nothing but the imaginary of the integral of grad chi grad u bar. Okay, and in all this singularity formation problem, the heart is that initially you really have no idea of what's the size of the gradient, right? You have no a priori bound on this quantity. You typically may know something on u, but this quantity here. So it's really the heart of the matter to either get estimates that do not see this, that in a way or another avoid this. If you look at the proof of minimal mass blow up for the L2 critical case by Mel, it's the heart of the matter. How can I do an estimate that does not see the fact that the gradient is sitting there? But as soon as you have, if you control the gradient, right, if you control, you have a bound on the gradient, allows us to understand how L2 fluxes evolve in time. And you understand my point. What I missed because because L2 is below, I don't have a conservation law in L2. I cannot use it. What I'm telling you is that this estimate, because I have something, I know I have a bound on what the gradient does, what I can show is that I can recover something like a conservation law. All I need to do is integrate on not too large interval in time. I need to localize this properly. So the bound, if you want, I'm going to call this the gradient bound. So the bound gradient allows you to treat L2 fluxes on parabolic time, on parabolic times are almost constant. Okay, so this would be what I would call proposition 2. So let's try to write something correct. Here it is. Okay, so proposition 2. So under the assumption of proposition 1, so that's the renormalization factor. Let lambda v of tau to be 1 over the L2 norm of the gradient of tau to the power 1 over 1 minus SC. That's the guy that renormalizes data to 1, and pick a time tau naught in 0 times tau over 2. Give yourself a bit of room. Okay, and assume something slightly more precise about the energy. Assume that lambda v to the twice 1 minus SC E of V naught is less than a quarter. Okay, I'm just precising what's over there. Let the parabolic scale, so let f star to be square root of T naught over lambda v of t naught. Okay, so you have to remember all I have is an upper bound on this. Okay, so this can be huge. Okay, but the self-similarity is precisely when this thing is of size 1. Okay, so what I claim, let d naught to be, so my data, so this is the size of the data, so m0 to some power, the max of 1, and this quantity f star. Okay, then, in fact, and that's the key, then when you look at the solution exactly at the size d star lambda v of t naught of v naught squared. So you see, so this is the size of the mass measure. So I don't know if it's parabolic. The enemy is parabolic. The enemy is really that lambda v of tau is less quality of tau. But a priori, I don't know it. Maybe the size, maybe I want to shrink at a much smaller size. But whatever this size is, this thing is lower bounded by a universal number. Okay, so this is concentration. And of course, this is a statement about the data. In other words, if you have lived so long, it's meant that initially you had to be large. Otherwise, you got. Okay, so this is really the key feature. This is the key. This is the key information that you bring things back to the data. So let me explain. Let me explain what's going on here. It's very simple. So how do you prove something like this? So proof. Oh, excellent. So proof. It's always the same story. It's just renormalization. So let me consider, so maybe this is step 1. So let me consider, so there is something that is completely trivial. So let me consider omega of x to be, I just renormalize lambda v to the 2 over p minus 1 at time t naught, v of t naught of tau naught, lambda v of tau naught of x. Okay, so I don't know what v does. I take a time tau naught in my time interval. I renormalize this guy, okay? And I do this in such a way, so this is the definition of lambda v of t naught. I do it in such a way that the L2 norm of the gradient of this guy is equal to 1. Okay, that's the definition of lambda v at time t naught. Okay, then what do I know about omega? Then I know I can compute the energy, of course. The energy of omega is nothing, so just by renormalization, it's nothing but lambda v of t naught to the twice 1 minus sc, the energy of v at time t naught. Okay, but of course, this is just energy is conserved, so this is just energy of data. And my assumption, which should be somewhere over there, this is here. So this is lambda v at time t naught. So this thing is telling me, my assumption is that this is less than a quarter. Okay, so this thing is just telling me that when if I take this v naught, I renormalize it by its size, I look at the renormalized object, the energy is less than a quarter. Okay, but of course, I can compute. This simply means that the omega p plus 1 norm, so this statement is just saying that it's equal to p plus 1 times half the gradient of omega squared minus the energy of omega. That's just the definition of the energy. And by renormalization, so this is 1/2, and I've decided that this is less than a quarter. Okay, so this is a non-trivial quantum. Okay, so this is a non-trivial number. Okay, so my renormalized guy, so when I look at my solution, I renormalize it, automatically the renormalized guy must have an LP plus 1 norm, which is non-trivial. Okay, so now pick say a small epsilon. So this is not what I want to conclude. What I want to conclude is that, in fact, I can localize this estimate. So let's take epsilon, A epsilon, to be some constant which may depend on epsilon, so the max. So I have a bunch of things that have been defined there, but these are just number that comes from the normalization. So I have f star and maybe m naught to another power. Okay, so I just take something that's sufficiently large with respect to this f star guy. So maybe I should erase this. Then what do I have here? Then what can I say about, I can look at the localized. What can I say about rho of omega at size A of epsilon? So it's equal to what? So by definition of A of epsilon, it's the rho norm at size of V. So this is scale invariance of the rho norm. So I can just write the definition of A of epsilon. So this is just the definition. So this is, I'm just using that A epsilon is the max and the rho norm is decaying. Okay, but what is this equal to? This is scale invariance. I know exactly what this quantity is. This is exactly the norm at the scale V of tau naught multiplied by m0 alpha 1. So I'm just using the rescale. This is just scale invariance. I know my rho norm is invariant. All it does is it changes the scale. But by definition of f star, this is rho of V of tau naught. So this is the definition of f star here. I have m0 alpha 1 square root of tau naught. And what have we learned? We've learned that this quantity, this thing is under control, right? This is my proposition 1. This thing is bounded by a constant, say, this is bounded by data. Okay, so you see, you take your object, you renormalize it. It has size 1 in the energy norm. The LP plus norm, the LP plus 1 norm must be non-trivial, and moreover, you control the rho norm, at least on a size, on a shell I epsilon, which just depends essentially on these quantities. Okay, but if this is the case, then indeed you can use, now you can estimate. So I'm afraid I will have to erase these things. So if this is the case, then you can estimate. You can estimate the far away. So if you look at the far away norm, you know, this is the point. This estimate allows you to understand what your omega looks like. So if you look at the far away norm, so this is just my interpolation estimate. So this is controlled by epsilon norm of gradient in L2, plus, and we said the interpolations will have a constant. I have a of epsilon to the twice 1 minus SC multiplied by the rho norm of omega at some epsilon to some power alpha. And now this is under control. So this is bounded by epsilon L2 norm of the gradient squared plus a constant divided by this A epsilon to the twice minus SC. So I can make this bounded. So this is 1, because the gradient has been normalized. So I can make all this be less than epsilon. I'm just taking A epsilon large enough. So what does it mean? It means that my rescale guy, it's not anything. Its LP plus 1 norm is non-trivial, but the far away part of the LP plus 1 norm is small. Okay, so automatically, this implies that the inner part, right, since the total LP plus 1 norm, remember, just by renormalization and energetic constraint, remember that the total LP plus 1 norm is bigger than 1, but we just said that we counted how far we should go. So we said the outer, it's the radial Sobolev, the outer is small. Okay, so I conclude that the inner, that's the key. This is concentration. I need to be the LP plus 1 norm must be big. Okay, but now I can just interpolate that. So I can think of it this way. I can say that this is less. So this is the LP plus 1 norm. But now I can do the stupid interpolation. You know, all I'm saying is that I can interpolate that by, say, constant. So, for example, I can interpolate this in L2. Yeah, I can just do, maybe I lose a bit of y twice less than epsilon. Maybe this is to the p minus 1 times 1. So I'm just doing my Sobolev here, times the gradient in L2 of omega. So I need to lose here twice plus p minus 1 SC. And maybe I lose. All I'm saying is I need to lose on the gradient, but I don't care because the gradient here has been normalized. Okay, so it means that this is, and plus maybe I need to allow myself to lose. I'm just localizing my Sobolev. So maybe I'm losing a p plus 1. But the only thing I want to say is that this is 1. Right, so what I've shown, what I've proved, is that the inner, it means that the inner L2 norm, if you want to, for x less than twice, the inner L2 norm must be of size 1. Okay, which means what? Which means when you go back to what omega is, it simply means that 1 over lambda v of tau naught, so the power is twice SC. I'm just coming back. So I have a size, I have an A of epsilon, such that if I look at the inner norm on this side for x less than A epsilon lambda v of tau naught, okay, of v squared at tau naught, this is bounded by 1. Okay, so this is, you understand, there is no dynamic here. All I've said is if my data at time tau naught, this is the end time, if my data satisfy this constraint here, because of the control of the rho norm, it's automatic that I renormalize this data. The energy is non-positive, but the gradient is small, but the gradient is of size 1. This forces the LP plus 1 norm to be large. But then the LP plus 1 norm, I have a control of what happens far away. So far away, I can make the outer. If you want, it's compact. Omega is compact. You see the large parts of the mass cannot be at infinity. It needs to be localized, and I know exactly how to count this. Okay, and now the key is that now you use the gradient bound. You simply use the fact that d tau of chi u squared is controlled by imaginary grad chi grad u bar. So it means what? It means that, again, this is something that's going to be controlled by grad u in L2 times the Morawetz companator. And I have my hands. I know how to control that. Right? It's my proposition 1. So it means what? It means that I know something on this at tau naught. This I know how to control, so I can bring this information back to 0. Okay, so I can bring the information back at tau equals 0 and realize that 1 over lambda v of tau. So at the scale tau naught, exactly the integral, the same information is true. I have an estimate of necessarily data had to be non-trivial there. Okay, but again, the key is exactly this. I look at my v of t naught, I renormalize it necessarily at t naught just because of energy constraint and control of my scale invariant norm. I have a non-trivial concentration of tau naught, and now because I control the fluxes, because I control the gradient, I can bring this information back to data, and necessarily my data, when I look at it at this size, it needs to be non-trivial. Okay, so I don't do this step, right? This is really just running the estimate that you did, but this is there is nothing more than plugging in your estimates here and integrating from 0 backwards from tau naught to a 0. Okay, so maybe we don't need more time to, maybe in the last 2 minutes I can show you, maybe the log I won't have the time. I'm just going to say a word about it, but I can just show you a proof of the Liouville theorem. Right, so what do we have? So let's say that we have, let's argue by contradiction. Okay, so I take an initial data which is non-positive, and I will assume, so it's in HSC intersected Hn dot, H1 dot, and I will assume that it leaves, say, it leaves on 0 plus infinity. Okay? Then the first thing I can do, I can apply my proposition 1. It's going to tell me something like this. It's going to tell me that this quantity is under control for all times. So tau star minus tau grad u of tau L2 squared d tau. You're going to find that this is bounded by a constant which depend on tau naught, tau star to the 1 plus sc. So I'm just applying directly my data, which gives me at least a sequence. It gives me a self-similar sequence. It gives me a sequence on which the L2 norm of the gradient must decay. This is my enemy. Must decay like 1 minus sc over 2. Okay, so this is, it gives me at least a sequence. So this is the self-similar bound.
Why can you stretch this estimate to large time?
Because that's my assumption. Tau star,
But you have a restriction on the size of tau.
energy is negative. I don't have a restriction. That's the beauty of this. My restriction was tau star to the 1 minus sc e of data less than equal.
It was a maximum between 1 and e.
Well, but that's probably so. But this is ridiculous, right? Because the energy. You're absolutely right, Igor. So let me just. Why did I? Oh, no, yeah, exactly. So what I said, I'm sorry, it was. I'm sorry, it's. I'm sorry, it's. You know, it's just because integration. It's a tau star. It's just in case the energy is positive. It's the max of E naught. I'm sorry, and 0, less than a quarter. Right, so if the it's 0. See, maybe I wrote 1, which is a mistake. It's just indicates the energy is positive. It limits the time which you can take. But if the energy is non-positive, right, this is automatic. Okay, so I can run this forever.
So in doing the localized Morawetz estimate
Yes.
and estimating terms on the right-hand side,
Yeah.
you don't need to. You can always go to large times.
Yes.
There's no problem with Groner.
With?
Groner, because you're using the left-hand side to control the right-hand side.
Absolutely. So it's exactly. So it's my rho norm on parabolic scales, controlled by 1 plus itself to a smaller power. This is the contraction. So you have to count all the time, but it's really a bootstrap. You start in a regime, it's of size 1. You assume it wants to reach 1 over epsilon, and you prove 1 over twice epsilon. That's exactly how. It's just interpolation. So scaling is not broken. You understand, but it's this power here that makes. Okay. So you get. So this is the first thing you get. So you get your self-similar decay. Okay, so if I look at okay, so it means I have a bound. So it means that, in fact, what does it mean? It means that if I look at, so I renormalize u by its size. So if I look at lambda u of Tn, this is exactly telling me, which is nothing but 1 over the L2 norm of the gradient of Tn in L2 to the 1 over 1 minus Sc. This is exactly telling me that this is lower bounded by time. Now there's a screw. Okay, which means the following thing, which means that the time which I call f star, which by definition was square root of tau n over lambda v of tau n. Okay, so this should be, this f star exactly are bounded by 1 independent of n. Okay, so what does it mean? It means that if I apply my proposition, so what does this mean for my data? It means that we have found. It means that if you want the A epsilon here, in fact, it's related to the F star. So in fact, it's uniform in n. It does not depend on n. Okay, so what does it mean? It means that I have exactly this. I have 1 over lambda v of tau n to the twice sc. The integral, so when I bring this back to data, the integral for x less than some universal value, I don't know, I'm going to call it d, lambda v of tau n of v naught squared, well, this thing I find that this is lower bounded by one independent of n. But if you give me a function, if you give me any profile, if you give me v naught in HSC, then it's completely trivial to see that 1 over r to the twice SC integral for x less than r of v naught squared, this needs to go to 0 as r goes to infinity, so it's impossible. You see, so the proof is very clear. Your initial data, it's global in time, so in fact the gradient essentially must decay, but when the gradient decay gives you control of the normalization, and the fact is so it gives you should think of it this way. It means that at Tn automatically v of Tn renormalized must be large, then you bring the information back to a data, so it means that on this scale data must be large, but this is a contradiction because when lambda v of tau n goes to 0, if my data is in the critical space, this is to go to 0. Okay? So I'm not going to show you the log proof. I'm just going to say the following words, and then we'll stop here. I'll just say that if you want to prove the log, the idea is the following thing. So you take a sequence t that goes to t, so where the gradient explodes. And so you know that the gradient explodes. And what you do is you do the following thing. You look at v of t of tau and x to be the renormalization. So you look at lambda u, you look at u of t minus lambda square u of tau. I'm sorry, this is a t, this is a tau, lambda u of t and x. Okay, this is a very nice object. So this is a double object. So t is a parameter. So lambda u is lambda u of t. So the idea is the following thing. So of course vt. So t is a parameter. So my initial data is such that at tau equals 0, this is lambda u over 2 lambda u of t, lambda u of tx. So this guy is normalized. Okay, and then, so it means what? It means that this, as t goes to blow up time, this gives you a sequence of initial data. Okay, and what you're going to do is that you're going to watch the sequence of initial data, and you're going to apply in black box the estimates that you have. And in fact, the fact that this initial data, you know where it concentrates on radius, which you essentially control, because you know exactly what's going on. Right? And it's by looking at the behavior of this thing that you will realize that this initial data, as time evolves, so it depends on time, t, but this initial data at time 0, you will find annuli, which are disjoint annuli on which this concentration must hold, and this is going to give you your logarithmic lower bound. So the point I want to make is that at the end of the day, you keep using only one estimate, which is always the same, control of the gradient, and control of the rho norm, and this estimate used extensively in different settings gives you the lower bound that you expect. The key is here, it's concentration. Okay, so thank you. We're done for today.